Hello, Chem 1132. I promised a video about Chapter 20. Now for those that were in class on Tuesday, you got many of the initial notes that are going to be in this video, but we did have quite a few absent, so I decided to make the video all about Chapter 20. Those that were in class on Tuesday could skip the first 4 sections up and maybe start at 20.5 in the video. So just scroll ahead to 20.5. All right, Chapter 20 kind of fits with Chapter 19. Remember, Chapter 19, we looked at the S and P orbital sections of the periodic table, the left 2 columns and the right 6 columns, and those were called the representative elements. And we just kind of surveyed them and looked at a lot of different properties of those representative elements, and that was Chapter 19, the most previous chapter. Now, Chapter 20 looks at the middle of the table. Remember, the upper middle of the table is the D block, known as the transition metals, and then the lower portion of the table, the last 2 rows of the table that are separated out way down below, are called the inner transition metals. So the D block and the F block. The inner transition metals consist of 2 rows, the lanthanides and the actinides. So let's talk a little bit about transition metals, and in the process we're going to look at coordination chemistry. We see coordination chemistry a lot with the complex ions. Complex ions being typically transition metal ions that then attach to ligands through a Lewis base, Lewis acid type of bond, a coordinate covalent bond. And these can have different coordination numbers. They can bond twice or 4 times or 6 times typically. And that's why it's called coordination chemistry. It's how many ligands are bonded to that metal ion. And of course, those would be aqueous typically. Metal ions in water. So these are the 8 sections we're going to go through. We're going to survey the transition metals. We're going to look at the first row transition metals, scandium through zinc, 21 through number 30. Then we're going to talk about these coordination compounds. We're going to look at how coordination compounds are named and how to maybe get a name from its formula, how to get a formula from its name. And we're going to look in 20.4 at how coordination compounds can form isomers, which are the same chemical formula but physically and geometrically put together in a different pattern. Then we're going to look at bonding in complex ions. We're going to look briefly at the localized electron model, but then show how the crystal field model allows us to talk about the magnetism and the colors of complex ions, coordination compounds in water. We'll look at the biological importance of coordination compounds in molecules such as hemoglobin and cytochrome and myoglobin, and we'll look at metallurgy, which is the science and engineering of ways of working with metals, particularly how to take metal ores and produce the pure metal from those metal ores being compounds, and then the pure metals being produced from those metal ores. Probably economically the most important one of those would be the production of iron and steel, so we'll look at that in detail as well. 20.8. Okay, starting with 20.1, we have the transition metals, just a quick survey of the transition metals. You'll find that within the transition metals, there's not as much difference from left to right as there are, or even in vertical groups, periods or groups. Neither one show a whole lot of chemical differences, maybe a few physical differences, but not a lot of chemical differences amongst the transition metals. We see a large difference in the representative elements. For example, you got the alkali metals, which are soft silvery metals, that react violently with water. Then you have the alkaline earth metals, which are a little less reactive than the alkali metals. And then you have your harder metals over on the right, and then they transition to nonmetals when you in the representative elements on the right side. And then eventually the last column is the noble gases, which are chemically unreactive. And so you see a large range of reactivity within the representative elements, but within the transition metals, a lot of similarities. And that's due to the valence electrons in the transition metals not being the last ones added. Typically, within a transition metal, you're going to add the s electrons to an outside energy level. And those are going to be your valence electrons. But then you're going to go back into a level that's one level closer to the nucleus, so one shell down from the outside, to add the D block. For example, in the first row of the transition metals, not the first row of the table, but the first row of the transition metals, you have 4s, and then you have 3d. 3d are the D electrons that are being added to the transition metals. So because you're not adding electrons to the valence shell, effectively what you're doing as you change atomic numbers from 21 to 22 to 23 and so on is you're adding a proton to the nucleus, but you're also adding an inner electron to the electron cloud, which in effect kind of cancels the attraction of the extra proton in the nucleus to the valence electrons through what we call the shielding effect. So the electrons on the outside of the atom feel the positive pull of the extra proton you added to the nucleus, but they also feel the repulsion of the extra electron you added to the level right below where the valence shell is. And so those two effects mostly cancel each other out, resulting in virtually no difference in the pull of the nucleus, the effective pull of the nucleus for the valence shell electrons. And as a result, a lot of similarities in the outermost electrons and how they interact with other atoms. So the chemistry of the transition elements is not affected as greatly by the gradual change in number of protons and number of electrons. And that's because you're adding electrons for the transition metals that are inner electrons, not valence electrons. They're the D electrons, the D block transition metals. And then for the lower inner transition metals, you're looking at the F block. The F block is actually 2 layers down from the valence shell. And since D and F electrons cannot participate as easily in bonding, and they cancel the effect of the extra protons you're adding to the nucleus as you go left to right, then the valence S and P electrons are fairly stable in their characteristics. So this is the portion of the table we're talking about. We're talking about this yellow part, the D block, and then this orange and purple part down below, the F block. That's the transition elements on the periodic table. Now, characteristics of these transition metals. A lot of times with the transition metals, you don't have one particular oxidation state. Iron can be +2 or +3. Copper can be +1 or +2. So unlike the representative elements where they have one oxidation state or one charge for their ions, the transition metals can vary in that, which is why we use that Roman numeral when we're naming them. Their cations can often form these complex ions. Complex ions are where a transition metal cation or positive ion is then surrounded in solution or maybe even in an ionic compound by ligands. Ligands are molecules or ions that behave as electron pair donors or Lewis bases. Remember NH3 in this picture, CO, NH3, 6. You have 6 NH3 molecules all surrounding that cobalt +3 ion. They're ligands. They're using the unshared pair on the nitrogen to make a coordinate covalent bond with the cobalt +3 ion. And that process is creating what is called a complex ion. So the cobalt and the 6 ammonias together as a 3+ ion, it's like this polyatomic ion on steroids there. It's called a complex ion. So typical example compounds could be something like CONH3 and then we put that in brackets because that is the complex ion. It has CONH3 3+, and then it's bonded to 3 Cl- ions, which are your anions. So you have your cation CONH3 plus 3, and then you have your anions, which are 3 Cl-1 chloride ions. And that is an ionic compound. Very complicated ionic compound. Another characteristic of these transition metals, particularly when they're in water solution, or they can also be when they're in the solid ionic form, is they often have color. And we're going to learn a little bit later kind of where that color comes from. And that's because the transition metal ion in the complex ion is going to absorb visible wavelengths of light. And by absorbing those colors, you're going to see a different color when you, of course, you don't see the colors that are being absorbed. Those wavelengths are gone, but you're going to see the complementary color, the colors that are not absorbed. You're going to see those colors blended to make the color of the transition metal ion. A lot of these compounds, even in the compound form, typically we don't see compounds that react to a magnet, but these compounds often do. Some of them do, some of them don't, but many of these compounds are what's called paramagnetic, something that would be attracted to a magnet. And that's because even as transition metal complex ions, they contain unpaired electrons, which allow them to be paramagnetic. So now we're going to look at the first row of transition metals, scandium through zinc. And we're just doing this group, this row, this period, I guess I should say. Groups are vertical, periods are horizontal. We're doing this horizontal row or period, and we're not going to go through all the others, like the second row and the third row, but you can assume that this sort of gives a set of examples that are typically going to be followed. In other words, these are representative of the other transition metal series. So, as far as the transition metals, these are the ones that typically are more common and have more economic significance. Things like iron and nickel and copper and zinc and these very important metals that we make a lot of stuff out of. Even titanium is alloyed with aluminum to make things like airplanes. So keep in mind the electron configuration and what we're talking about here. In the transition metals, we're looking at 3D orbitals. But these 3D orbitals are being filled after the 4s orbital was complete. Potassium and calcium complete the 4s1, 4s2. Then scandium picks up with 3D1 and titanium 3D2 and so on. So we're not talking about so much valence electrons, that's the 4s. We're adding electrons to an inner level, a sublevel called the 3D. So your first metal, scandium, going to have one electron in the 3D orbitals, 4s2, 3d1. The second metal, titanium, is going to be 4s2, 3d2. Vanadium, 4s2, 3d3. And then you would expect chromium, Cr, to be 4s2, 3d4. But the 4s and 3d have very similar energies. And because you have one of the d orbitals that has nothing in it, remember 3d4, there are 5 d orbitals, so only 4 of them have an electron in them, and the 4s2 is doubled up. You might remember that doubling up causes repulsion. It is actually, this is the first atom on the periodic table that does not follow the pattern of that typical 1s2, 2s2, 2p6, 3s2, 3p6, that pattern we learned, remember that had the diagonal rule with the chart and and the arrows that you would follow. This is one that you'd actually not get the correct electron configuration if you just followed that pattern. 4s2 3d4 is what you expect, but to minimize the repulsion in the 4s, you actually move one of the 4s electrons to the empty 3d to make 4s1 3d5. And so instead of having 2 paired electrons and 4 singles, you have 6 single electrons. So chromium going to have some magnetic properties there. Copper also you would expect to be 4s2 3d9. But again, to minimize that repulsion in the 4s, we actually move the electron to the 3d and we have 4s1 3d10. So those two atoms in the D block actually show exceptions to the filling pattern that you would expect for electron configurations. There are more exceptions as you go down the chart, but this is the first two that we see that do not follow the pattern perfectly for its ground state electron configuration. So here is a table. It lists elements 21 through 30, scandium through zinc, gives their actual electron configuration, even the exceptions, chromium and copper, gives the atomic radius. So you can see by looking at this that maybe with the exception of scandium, everybody's in that 120 to 140 range with their with the size of the metal atom or the atomic radius of the metal atom, and we don't see the typical drop in atomic radius that you would normally see left to right. We see a little bit of fluctuation, 162, 147, 134, 130, back up to 135, back down to 126, down to 125, 124, back up to 128, back up to 138. See, it's not perfectly following any particular pattern. You can look at some ionization energies, which can help you with the relative ease of taking one electron or two or three from each atom. That can help you understand why you get certain common oxidation states. The reduction potential, we'll save discussion of reduction potential to our chapter on electrochemistry, but it has to do with the tendency of this metal atom to lose electrons or not compared to other atoms. And then we have our melting points, which have to do with how strongly the atoms hold together with their metallic bonds. Their densities, and you might see there is an inverse relationship between atomic radius and density. But we also see a left or right pattern of typically increasing density. So remember, left to right, the atoms are getting heavier. So the mass, the numerator for density is mass over volume, the numerator is increasing left to right. But the volume isn't being consistent. The volume is going up and down and up and down. So when we see a high atomic radius, that means that the atom takes up a lot of space, which means a gram of the atoms is going to take up a lot of space. And so, for example, our largest and our lightest but largest atom, scandium, it's got the smallest atomic mass of the group, or of the series or row. It's got the smallest mass but the largest radius, so it's got the lowest density. That's because density is mass divided by volume. It's a ratio of mass to volume. And then we have the electrical conductivity. Copper is actually really, really high in electrical conductivity according to this table, and according to real life, because copper is the second best conductor of electricity behind silver, and that's why we use copper wires in our walls to carry electricity, and copper wires on our poles to carry electricity to our homes. Is because copper is such a good conductor of electricity. All right. The energy for the 3D orbitals is less than the 4s, and that's why we fill up the 4s before we start in on the 3d. But when we take the electrons away, we do not take away the 3d electrons first. We first typically remove the 4s. So when you're asked to come up with the electron configuration of an ion, remember you're always removing the valence electrons, not necessarily the last one in, doesn't necessarily have to be the last one out, because in the case of the transition metals, the 3d electrons are the last ones in, but the 4s electrons are the first ones out when you form the ion. Neutral titanium is 4s2 3d2. But if you form a Ti plus 3 ion, you're going to take away the 4s2, and then after the 4s2 is gone, now the third energy level becomes the outermost level, and you would take away 1 from the 3d to get your plus 3 charge. Remember, you take away 2 to get the plus 2 charge with the 4s. 1 more from the 3d gets you the plus 3 charge that you're looking for in this titanium plus 3 cation, which has an electron configuration of argon 3d1. You've lost the 4s2 and 1 of the 3ds. Manganese, the atom, would be 4s2 3d5. Manganese plus 2 is just 3d5. The plus 2 means you've lost 2 electrons. The 2 you would lose would be the 4s, not the 3d electrons. So scandium plus 1. All right, so scandium plus 1. Scandium, the atom, would be 4s2 3d1. And I would expect scandium plus 1 to be 4s1 3d1. But they are calling it 3d2. So I need to look that up and figure out why it's not the pattern we would expect, because the atom, scandium, is 4s2 3d1. So if you take away 1 electron, you should be taking away 1 4s electron. So it'll be 4s1 3d1. So maybe in class I can have some time before class to get that figured out. Why it's 3d2, not 4s1 3d1. All right. For the first 5 metals, your maximum possible oxidation state should be how many electrons you have in the 4s and the 3d. You're not going to mess with the 3s and the 3p electrons to make your cations. So your highest possible oxidation state for a transition metal ion is going to be how many electrons you have in your 4s and 3d. So if you have 5 electrons in the 4s and 3d, such as vanadium 4s2 3d3, you would not expect vanadium to have an oxidation state any higher than plus 5. As you get toward the right end of the period, you typically don't see them taking advantage of their possible maximum. Zinc would actually have a possible maximum of plus 12, but you never see plus 12. In fact, probably the most common oxidation state toward the right end of the period is going to be plus 2. And that's because you've got nuclei with a lot of protons in them holding onto those 3d electrons pretty tightly. Higher oxidation states typically are not seen. Those 3d orbitals are lower in energy as your nuclear charge increases. Electrons are getting harder to remove. Here we see the first and third ionization energies for your first row transition metals, and right away you see that it is much harder to remove the third electron than it is the first. So remember, the first electron is coming from the 4s. The third electron is going to always be coming from the 3d. So the 3d electrons, harder to remove than the 4s. And increasingly hard as you go to the right. So you typically don't see zinc or copper losing more than the number of electrons they have in the 4s. All right, here's your reducing ability. Scandium is the best at giving away electrons, and copper atoms are the worst at giving away electrons. This is a table that we will then later in the electrochemical part of the class, we're going to use this table to develop the idea of batteries and how you can take two reactions and make a chemical battery that will transfer electrons. Okay, now the 4D and the 5D, which would be the yttrium through cadmium and the lanthanum through mercury. The 4D and the 5D, you're generally going to see the atomic radii increasing as you go down from scandium to yttrium and so forth. And you're going to see quite a large increase from the third row to the fourth, but not so much from the fourth to the fifth. The 4D and the 5D metals are remarkably similar in size. They're very similar in size. And that is due to an effect called the lanthanide contraction. Typically, as you go down the chart, you see an increase in size. But remember, in the sixth row, which is where we have the 5D, before the 5D electrons are filled, you have the 4F orbitals in the lanthanide series being filled. So you have 14 electrons that go in and 14 protons that go in before you get the 6D. So typically, as you go down the chart, you see an increase in size. Left to right, you see a decrease in size. So because the sixth row has 14 extra positions in that row, or 14 extra additions of protons to the nucleus, before the 5D electrons get added, and that's not something you see in the fifth row. You go straight from 5s to 4f, or 5s to 4d. In the sixth row, 6s, 4f14, 5d10. So while you're adding protons and electrons in that 4f14, you're actually seeing a gradual reduction in size due to the additional protons you're adding to the nucleus. And so what you have there is an increase going down, which is then counteracted by the decrease as you fill in the 4F, resulting in a lot of similarity in size between the 4D and the 5D elements due to that thing called the lanthanide contraction. And here it is graphically shown. You see that the green is, there's a decent gap between the size of the green and the size of the blue, which are your first and second series, your 3D and your 4D. But the red sits almost right on top of the blue. There's very little difference in size between the 5D elements and the 4D elements. Lanthanum through gold are about the same size atoms as yttrium through silver. The reason why we don't see the same gap between 4D and 5D is that lanthanide contraction. See, before you get to this D, you had to fill up an F orbital with 14 electrons, and to do so you had to add 14 protons, and those 14 protons shrunk the atom enough that you don't see the increase in number of energy levels having a big difference in the size of the atoms. Okay, 20.2, we're going to look at the first row transition metals. First row transition metals, scandium through zinc. Scandium. Scandium's chemistry is similar to the lanthanides in that it's colorless and diamagnetic. So scandium does not have the property of the other transition metals of having color and having paramagnetism. Colorless and diamagnetic. Not enough electrons in the d orbitals to really get those d orbitals cranked up and doing what they do, giving paramagnetism and color. Titanium. Titanium atoms in the solid form are excellent structural materials. They have low density but high strength. So kind of like aluminum. In fact, titanium and aluminum alloys are used in airplanes because of their low density and high strength. They're light and strong. Vanadium is also used in many alloys with other metals, often transition metals. Chromium, another element that's used in alloys such as stainless steel, but also used as the pure metal. We see it in anything that's got chrome. We say chrome mirror, chrome, the chrome fixtures in a bathroom. These shiny silver chromium metal has the ability to form a very thin oxide coating or rust coating on it that is actually clear. So unlike iron rust, which is red, brown, and ugly, the chromium rust is actually kind of clear like glass. And so it's almost like it's its own clear coat, and it's very hard, and that clear, hard coating on the chromium metal keeps it shiny and keeps its luster, its shiny luster, for a long time, and you rarely see a chromium rusting. So you can actually plate chromium. You can put chromium on the surface of other metals, and it will help keep them from getting rusty, and they'll stay nice and shiny and silver and pretty. Manganese, it's one of the elements that's alloyed into very hard steel. Iron, this is our one that we make into steel, so it's a very important economic element. Cobalt, also used in alloys like stainless steel or stellite, also in stellite. Nickel, you can plate nickel on top of more active metals, and you can make alloys with nickel. Nickel plated on more active metals can keep those more active metals from corroding. Copper has plumbing and electrical applications, so we see it in copper pipes and we see it in copper wires. Zinc mainly used for galvanizing steel. So if you coat steel with zinc, the zinc will rust first. It's more chemically active. It's higher on the activity series, as we saw in that lab we did last week. So galvanizing steel, the zinc will sacrifice itself so the steel doesn't rust. The zinc will rust instead. And so that can keep you from getting that red-brown rust and rusting through the steel if you put some zinc on it, and that's called galvanized. So looking at some oxidation states for different species, here's vanadium. Vanadium has 5 electrons, 4s2, 3d3. So your oxidation state for vanadium is going to max out at +5. And we see different colors for vanadium with different oxidation states in water. We have the V2 plus ion, the V3 plus ion, the VO, vanadium and oxygen 2 plus ion, it's blue. So we're going to learn that these colors have something to do with the d orbitals of the 3d orbitals for vanadium and for other transition metals that have color. Here's chromium, +2, +3. Notice it maxes out at +6 in potassium dichromate and sodium chromate and CrO3. And again, we have these red colors. Manganese is going to max out at +7. Potassium permanganate, actually the manganese in that compound has an oxidation number of +7. Here's iron. Now we're starting to get over toward the right side of the table where the electrons in the d orbitals are held more tightly, and so we don't see these very high oxidation numbers being witnessed here. Iron is only going to be +2 or +3. +2 or +3. Cobalt, again, +2 or +3. And a lot of different colors depending on what it's bonded to and what its charge is. Nickel, just +2. Nickel kind of looks silvery like an actual nickel. A 5-cent nickel is made of nickel metal. But in its corrosion form, it can get a greenish or blackish or bluish or yellow color to it. Copper has various alloys that you find in copper in. It's a big part of brass. Copper and zinc are the main components of brass. Copper and tin make bronze, and maybe a little bit of other elements blended in. Sterling silver is a mixture of copper and silver, and then different carats of gold will have copper and silver alloyed with the gold. 18 karat gold is actually only 75% gold. It's 5 to 15% copper and 10 to 20% silver. Typical compounds, you're going to have oxidation state of +1 or +2. Copper can be +1 or +2 in various colors. Okay, moving on to section 20.3, we look at coordination compounds. So coordination compound is going to be a complex ion, and then that complex ion is going to have counter ions. And by counter ions, if the complex ion is a cation, it needs anions to be its counter ion. If the complex ion is an anion, it needs cations to be its counter ion. So a complex ion will have counter ions. And that's the ions that give it the 0 overall charge. For example, this is not a coordination compound, but in an ionic compound like calcium chloride, CaCl2, the calcium is Ca plus 2, the two Cl minus 1s help it add up to no net charge. So we would say that the calcium is the counter ion of the chlorides, and the chlorides are the counter ion of the calcium. So 3 examples of coordination compounds would be this cobalt with 5 ligands of ammonia and 1 ligand of chlorine attached to it. So it's got 6 ligands attached to it. And then it overall has a charge of +2. So your complex ion is +2. So you're going to need 2 Cl negative 1s as counter ions to balance out its charge and give you the entire coordination compound formula. Here we have 2 ions of iron with 2 ethylene diamine, which are bidentate ligands. In other words, they bond twice. And then we have the 2 of the nitrites, NO2 minus 1s. And that complex ion is saying twice, so it must be a positive 1, because 2 positive 1s would be counter-ioned with 1 SO4 minus 2. Your most common charge for the complex ion is positive. They're typically the cation, but they can be the anion, as we see in K3FeCN6. K3FeCN6 has a formula in which the K is the positive counter ion, FeCN6 is the negative complex ion. Okay, I'm going to stop the video here, and I will pick up here with the second installment of this video, so we'll call this installment number 1 for chapter 20. And I'm going to stop here and post this video, and then I'll post the next installment, which may be the rest of it. I may have to break this into multiple installments, but I'll post the rest of the installments, and together you can watch the different videos and see the entire chapter 20. But I'm going to stop on this slide right now.